So it's my pleasure to introduce Reverend Dr. Rodney Holder, who was formerly the course director at the Faraday Institute. He is a regular speaker here still, even though he's retired. We're very grateful that he keeps coming back. He's obviously not fed up of us. He is a Byfellow at St Edmund's College and a Faraday Associate. His first degree was in mathematics, and then he moved in Cambridge. He moved into astrophysics at Oxford, worked in operations research for a while before retraining in theology and training for the pastoral ministry, and has worked in a number of places, including Heidelberg. And Rodney's going to speak to us today about Is the Universe Designed?
Thank you, Ruth. Well, I'm going to start with this picture, and I'm sure you all recognize the person on the right, Albert Einstein. The person on the left is less well known, but he is one of the greatest cosmologists of all time. His name is Georges Lemaitre. Last year was the 50th anniversary of his death. I was invited, for example, to a conference in Rome at the Belgian Academy to commemorate this great man. He being a Belgian priest, a member of this very college from 1923 to 24, and someone who solved Einstein's equations of general relativity, that is Einstein's theory of gravity for the universe as a whole, and came up with an expanding universe solution initially, and then what he called the primeval atom in 1931, an expanding universe that expanded from a hot initial dense state. Science and religion in conflict? Well, pull the other one. The Big Bang was predicted from Einstein's equations by Lemaitre, and it's extremely well supported by evidence. The expansion was the initial evidence that came along. That wasn't good enough for certain cosmologists here in Cambridge, Fred Hoyle and others, who didn't like the idea that the universe had a beginning, which is what the Big Bang indicated, and proposed an alternative steady-state model, whereby the expansion is explained by saying, well, in the space between the galaxies, new matter comes into existence as they move apart at just the right rate, so new galaxies form, and the universe is the same yesterday, today, and forever. A phrase which we will have another take on, I think, in this room. Anyway, in 1965, they discovered, two guys called Penzias and Wilson, here they are, discovered the cosmic background radiation, which is the remnant radiation field from the origin of the universe. It's at 3 degrees above absolute zero, minus 270 Celsius. It's very cold out there. It was predicted on the basis of the Big Bang by American cosmologists back in 1948 and then observed. And interestingly enough, Lemaitre heard about this on his deathbed just before he died, that the clinching piece of evidence had come for his theory. And I'm just going to give you a flavor for what we're talking about in cosmology now. That's a typical galaxy, 100,000 million stars, and there are 100,000 million galaxies in the observable part of the universe. This is, I think, an extremely interesting picture. It's the Hubble Ultra Deep Field. Each of these little blobs is a galaxy. And what we're observing here are galaxies that were the first to form in the universe. And because light takes 13 billion years to get to us, we're looking at the universe as it was when it was 5% of its present age of 13.8 billion years. So I think that is a truly stunning picture taken by the Hubble Space Telescope. Now, the story of cosmology goes like this. As space expands and you get these instabilities formed by gravity called galaxies, and within them stars, the first generations of stars consist of hydrogen and helium, and all the other chemical elements are built up inside the stars through nuclear reactions. And when the first generations of stars come to the end of their life, they've burnt up their nuclear fuel, they explode, and the chemical elements that they built up are spread out into the surrounding medium so that the next generations of stars can have planets and ultimately life. So the building blocks for life are built up inside stars. This is a typical example of a supernova, Crab Nebula, observed by Chinese astronomers in 1054, but this wonderful picture again with the Hubble Space Telescope. This is another kind of example of the same sort of thing with a shock wave from the central star spreading out into the surrounding medium, giving this necklace effect. Now, it seems to me that the Big Bang poses, or potentially raises, two interesting questions that may relate to theology. And the first is, well, it looks like the universe began to exist. That's what the Big Bang theory is saying. And the second is that it looks as though it's been set up in a rather special way. That's the so-called fine-tuning. The first of these really relates more to, if you like, the cosmological argument for the existence of God, and the second to the design argument in traditional terms. I'm going to say a bit about the first one, and then rather more about the second one. So what do we make of the beginning? Well, back in around 400 AD, St. Augustine said this: "Assuredly the world was made not in time, but simultaneously with time." So for Augustine, the whole universe, space, time, and matter came into existence together. They're intimately connected. And that seems to be, interesting enough, all these millennium and a half later, what the Big Bang theory is saying. Although in his book, The Grand Design, Stephen Hawking has a very, very peculiar take on Augustine. And indeed, Stephen Hawking, he thinks that Augustine is perfectly, is compatible with a creationist, view, a seven-day view, and so on. But in fact, it seems to be entirely compatible with the Big Bang. But be as it may, Hawking, like Hoyle and others before him, doesn't like the idea that the universe had a beginning, because he thinks, so long as the universe had a beginning, we could suppose that it had a creator. But if the universe is really completely self-contained, having no boundary or edge, it would have neither beginning nor end. It would simply be. What place then for a creator? Now, I think he's a great scientist, a great cosmologist, but not a great philosopher or great theologian. So he sees the only role for God as lighting the blue touch paper, as it were, at the beginning and then letting it run. Which is certainly not how we see God as creator. But let's carry on with this. Back in, this man called Alexander Vilenkin, a colleague of Hawking's, so Hawking, just go back to the Hawking's no boundary proposal for a minute. He has this very interesting theory whereby as you track back the history of the universe in time, as you get very, very near the beginning, time becomes imaginary, and it's a very difficult concept to get your head round. Time becoming imaginary, what it really means is that time becomes like another space dimension. So instead of 3 dimensions of space and 1 of time, you have 4 dimensions of space. People who've done maths and know about complex numbers will understand this sort of thing. But it's very peculiar, both philosophically and indeed scientifically, that time should become like another space dimension, because time, real time, is what measures how you change state. So from one state to another. So if there's no real time, you wonder how the universe might just be, as Hawking puts it, but how does it get to be at another state? Well, subsequently, but then what does subsequently mean if there is no... Anyway, so he's tried to avoid the beginning, but back in 2012, to celebrate Hawking's 70th birthday, there was a symposium held in Cambridge to honour Hawking. Sadly, he couldn't be there himself because he was ill. And very sadly, with my conference in Rome that I've just been to, he was supposed to be speaking to us, but again was taken ill. He got to Rome and met the Pope, but couldn't be at our conference. Anyway, he couldn't be at this one, and he's just turned 75 too now. You know, this is astonishing given his physical disability. But anyway, at the conference in 2012, his colleague Alexander Vilenkin demonstrated what he called these singularity theorems, which show that as you track back the history of the universe, if you take a light ray or something like that and track back its history, it will always come to an end. And so there will be a beginning to the universe. And all the evidence we have says that the universe had a beginning, is what Vilenkin said at that conference. Now, St. Thomas Aquinas, interestingly enough, back in the 13th century, said that by faith alone do we hold, and by no demonstration can it be proved that the world did not always exist. So he did believe that the universe had a beginning, but this wasn't actually necessary to his arguments for the existence of God, his 5 ways, if you like. What he's talking about there is a first cause, a necessary being, and so on, which I'll talk about a bit in a minute. The universe could, in principle, have an infinite past, but you would still need a creator to create that whole infinite sequence. You need a creator outside the system, as it were, to create it. Now, cosmologists have come up with some interesting ideas in recent years, and here's another man, Lawrence Krauss, who wrote a book called A Universe from Nothing a few years ago, and I had the privilege of debating with Lawrence Krauss on Premier Radio, which was fun. Anyway, Krauss and also Hawking make statements to the effect that the universe creates itself out of nothing. And this is really a rather strange thing to say. If it sounds paradoxical, it is paradoxical. What Krauss basically redefines nothing to be a rather sophisticated something, the quantum vacuum. And the quantum vacuum is very far from nothing. It's a hive of activity with particles instantly coming into existence and annihilating instantaneously and so on. It's a hive of activity. It's very far from being nothing. The vacuum, according to Krauss, has lots of properties, including the property of being unstable. How can nothing have any properties at all? It seems to me that this line of argument is rather like this one in Through the Looking Glass, with a slightly different confusion, but this is the way it goes in Through the Looking Glass. "I see nobody on the road," said Alice. "I only wish I had such eyes," the king remarked in a fretful tone, "to be able to see nobody. And at that distance too." "Who did you pass on the road?" the king went on, holding out his hand to the messenger. "Nobody," said the messenger. "Quite right," said the king. "The young lady saw him too." "So, of course, nobody walks slower than you." "I do my best," the messenger said in a sullen tone. "I'm sure nobody walks much faster than I do." "He can't do that," said the king, "or else he'd have been here first." Now, you see here the distinction between nobody in the sense of the absence of any person at all, and a Mr. Nobody with a capital N. Well, it seems to me that Krauss and others are making precisely that mistake, same mistake, but with a nothing and a nothing, a capital N nothing that has lots of properties. Okay, so coming back to the Christian doctrine of creation then, that seems to me to be the answer, not really necessarily about the temporal beginning, although present science seems to be telling us that there was one, but more about why there is something rather than nothing. And Aquinas says that only God can provide that kind of explanation because God is necessary being. And by necessary, he means that God cannot not exist, if you like. God is eternal. There never was when God was not. So the Dawkins question, well, who made God then, is a meaningless question, because something that is made, that comes into existence, is not God. That's not what we mean by God. You can debate about whether this necessary being God exists, but if God exists, as necessary being, then he explains why everything else exists. And everything else is contingent. It may or may not have existed, could be different from what it was, and so on. That's the case with the universe. And interestingly enough, this point seems to have been recognized by various cosmologists, including Stephen Hawking, who expressed it very beautifully when he wrote A Brief History of Time, because what he said was, what is it that breathes fire into the equations and makes a universe for them to describe? Yeah. You can have the most wonderful physical theory. Hawking and others are searching for what they call the theory of everything. Well, it's a bit of a misnomer. But anyway, you can have the most beautiful theory of everything, the most beautiful physical theory. Why is there a universe to which that theory applies? And that is a question that is beyond science's capability to answer. It's a metaphysical question. Science always starts from something and sees how that something evolves over time. But why there is the something at all, whether backwardsly eternal or with a temporal beginning or not, that why question, why is there a universe at all, is metaphysical, and there is a theological answer to it, but not a scientific one. Okay, well, let's hope I've helped to sort of clear up some issues on that point. But then let me come to the so-called fine-tuning. The universe looks special. And that's to do with both the initial conditions, the way it was set up right back at the beginning, at the Big Bang, and the constants that go into the laws of physics. And these constants are things like the strengths of the fundamental forces of nature, gravity and so on, the masses of the fundamental particles. And it turns out that if you were to change these things by tiny amounts, you would get a dead, boring universe. Cosmologists play with their mathematical models, and they describe models that evolve in different ways. And if you were to change these numbers, as I say, you'd get a completely different universe, one that was dead, boring, no life, usually nothing of interest at all. Okay, so let me give you a few examples of this sort of thing. So the mean density of stuff, of mass energy in the universe, 1 second after the Big Bang, track back the 13.8 billion years to 1 second after the origin, needs to be what it was to 1 part in 10 to the power 15. That's 1 with 15 noughts after it. Now, the universe is sitting on a knife edge between expanding forever and ultimately recontracting to what gets called a big crunch. Okay, and this, which outcome you get depends on this mean density of stuff. If the mean density is above a certain critical value, then the universe will recollapse. And if it's above by more than 1 part in 10 to the 15, it'll recollapse far, far too quickly for anything interesting to happen in a matter of months. Similarly, if the mean density is below the critical value, then gravity won't be strong enough to pull it back. It'll expand forever. And if it's below by more than this critical amount, at that time, then the universe will expand far too quickly for the instabilities to form and form galaxies and stars and so on. And you can track back that figure even earlier to a fraction of a second, and the 1 part in 10 to the 50 gets expanded to 1 in 10 to the 60. High degree of accuracy at the earliest time we can speak of. Right, the weak nuclear force and the gravitational force. The weak nuclear force is that's responsible for radioactive decay. And if there isn't a really special relationship between that and the gravitational force, then in the Big Bang, all the hydrogen will turn into helium. You're bequeathed from the onset hydrogen. In the first few minutes of the universe's existence, the 25% you end up with hydrogen turning into helium, and you get a balance of 75% hydrogen, 25% helium. That's an interesting fact in itself, because I was talking about how most of the chemical elements are built up inside stars. Cosmologists couldn't work out how the helium got formed, and the other place where you get the same kinds of conditions of very high temperatures and so on, where nuclear reactions occur, is in the Big Bang, and that's when the helium was formed. Now, if this relationship were altered very, very slightly, all the hydrogen would be turned into helium, and then you'd get no chance of life, because there would be no hydrogen left, no water could be formed, and so on. And then there are other constraints on this relationship as well, to do with the supernovae explosions I was mentioning about. Supernovae wouldn't blow off their envelopes unless this relationship were more or less exactly what it was. And then you couldn't get the elements spread out so that you could get planets and life ultimately forming. My third example is that the strength of gravity. Now, this needs to be very close to what it is. Well, up to a factor of maybe 3,000 times its actual value in order for life to occur. You can have gravity increasing to a certain point. What starts to happen is then, well, beings our size, on planets our size, get crushed and couldn't exist. So you couldn't have creatures with our kinds of brains on a planet our size. Okay, you can compensate for that a bit by shrinking the size of planets, but then ultimately you get to a planet that couldn't sustain an ecosystem. It's too small, and so on. Now, in principle, the strength of gravity could be 10 to the power 40 times its actual value. So if you do a sum, you can work out the probability, naively speaking, about the gravity lying within the life-conducive range is 3,000 divided by 10 to the 40, which is 3 times 10 to the minus 37, a very, very tiny probability if gravity were chosen randomly. Now, my fourth example is, I think, the most interesting of all, and that is to do with the strong nuclear force, which is the force that binds atomic nuclei together. Now, that has to be just right in order for the chemical elements to be built up in the kind of way I'm talking about, in particular for carbon to be formed inside stars and oxygen. Now, carbon, these are essential for life, of course. Now, if a carbon is formed by crashing 3 helium nuclei together, and it's very difficult because the intermediate element of beryllium, with just 2 helium nuclei crashed together, is unstable. It only lasts for a tiny fraction of a second. So you've got a tiny fraction of a second to crash the third one on. And that requires a special effect in the carbon atom, an energy level, a particular energy level called a resonance, at a particular energy. Now, you then don't need a similar resonance in the oxygen atom, because if you did, then all the carbon would turn into oxygen. So you need, and this depends very critically on the value of the strong nuclear force to get both carbon and oxygen inside stars. Now, the reason I say this is particularly interesting is that it was discovered by none other than Sir Fred Hoyle, advocate of the steady state theory, a militant atheist. He made broadcasts on the BBC in the late 40s, early 50s, in which he described religion as an illusion. I've just come back from Ireland, and indeed I was in Northern Ireland 2 years ago for a conference, and I told this story then, and maybe it's becoming more critical now even. But Hoyle would have solved the Northern Ireland problem by locking up all the Catholic priests and locking up all the Protestant ministers and throwing away the key, because they were teaching rubbish to their congregations, and it was different rubbish. So this is a man who didn't like religion. But anyway, he was moved to say this when he made this discovery, that a super intellect has monkeyed with physics as well as with chemistry and biology, and there are no blind forces worth speaking about in nature. super intellect. I mean, if we were St. Thomas Aquinas going through our 5 ways, which we're probably all familiar with anyway, you know, he ends all of them by saying, and this we call God. Well, of course, Hoyle couldn't quite bring himself to talk about God, but nevertheless, the universe is a put-up job, he said. Otherwise, you're left with a monstrous sequence of accidents. The only way to avoid that is to say that a super-intellect is behind the laws of physics and chemistry. This is Paul Davies, a very notable cosmologist who's written about this and thinks that it's certainly something that is mysterious, that needs explaining, this fine-tuning. And he says that like the porridge and the tale of Goldilocks and the 3 bears, the universe seems to be just right for life in so many intriguing ways. Now, how do we explain the fine-tuning then? Well, I suppose, you know, if we're believers, if we're theists, if we're Christians, then we might say, well, you know, God's set it up, and because God intended there to be life, intelligent life, creatures to come into existence who would be able to relate to him, and so on. But suppose we're atheists for a minute, and we want to avoid this kind of design argument. What alternatives are open to us? How do we explain the fine-tuning? Well, I think there are 2 main strategies. One is to say that, well, maybe I'm wrong. Maybe these numbers that I've been talking about, the strengths of the forces and so on, just have to be the way they are. Maybe we'll get some more fundamental theory which explains them. And they're not variable at all. The second strategy is diametrically opposite to that. It's to say, oh yes, the constants and so on can take other values, and indeed they do in a multiverse, which is a giant collection of universes, usually infinitely many universes, in which all the constants take all the possible values they should, and so the argument goes, well, we shouldn't be surprised to be in a universe that's like ours, that has the right conditions for us to be here, because, well, we couldn't exist in all the others. But we do only exist because all the others exist, all the other universes exist. Now, again, it seems to me that there are problems for each of these atheistic strategies. There are really 2 versions of the first one. The first is, we're talking about the same laws of physics that operate here, but we might end up with calculating all those numbers that I've talked about, and they have to take the values they do. There's an even more rigid version of that, if you like, which says that there's only one self-consistent set of laws anyway. But either way, it would seem to me to be a surprise that the only self-consistent set of laws, or the theory of everything that calculated the numbers, what gave rise to a universe that is conducive to life. Because we can certainly imagine lots of other universes, lots of dead and boring universes. And why is it incoherent to suppose that they couldn't exist? Even if those numbers necessarily take the values they do, it would be surprising that that was the life-bearing universe, the only possible universe. For atheistic strategy 2, the multiverse, well, you still have to ask why this multiverse as opposed to another. And it seems to me with both kinds of explanation, you are shifting the question, if you like, from why do the constants take the values they do to, well, why is it this set of laws that applies, that gives rise to these constants? Why out of many sets of laws is it this particular set of laws? With the multiverse, there's a similar question, though. Why this multiverse as opposed to another multiverse? Because there are lots and lots of different ways of getting multiverses. There are even lots and lots of different ways of getting infinitely many universes. I shall come to a point about infinity in a moment, but I think there are some paradoxes there to do with infinities, which I'll mention. Anyhow, recent developments in cosmology seem to alternate between these different kinds of explanations. So here's a chap called Alan Guth, who a few years ago came up with a theory called inflation. And what that postulates is a very rapid period of expansion. This is time along here, and this is the size of the universe, if you like. The universe expanded very, very rapidly in the first 10 to the minus 32 seconds, very tiny fraction of a second from the beginning. And then you've got the gentle, normal Big Bang expansion after that. It's slowing down, but then this indicates that it's speeding up again, and that's something to do with the cosmological constant, which I'll mention in a moment. Now, what this theory does is that it drives the universe to uniformity, or our neck of the woods, a much bigger, gives a much bigger region that is uniform and in which the density is very close to the critical value, even equal to the critical value. And so it solves, if you like, one of the fine-tunings, that initial condition of the density. But it does so at the expense of needing fine-tuning in itself. So this theory needed to be fine-tuned in order to do the trick. So my point is that you've shifted, as I was saying, you've shifted the question just up a level to now why inflation is fine-tuned. So the answer that cosmologists have now come up with, Guth and others, Andre Linde at Stanford, is multiverse versions of inflation. So chaotic and eternal inflation. What these say is essentially you have an overarching space-time in which there are lots of different regions, some of which inflate, and then within these different inflating regions you get other universes bubbling up out of them, and so you get an eternal and these universe in the future anyway, it'll still backtrack to an initial point in the past, all of this, according to Vilenkin's theorems. But anyway, you get a multiverse version of inflation. All these different regions are called universes in their own right, and that's because our universe can't have any contact with any of the others. We can't observe them. The background space is expanding too fast and so on for any signals to reach us from them, and so they are unobservable. Now, we're not quite at the so-called theory of everything yet, but this is a man called Leonard Susskind who has pioneered, one of the pioneers of string theory. That's a theory, it's a candidate theory for the theory you need right back at the very, very beginning, the first 10 to the minus 43 seconds from the origin, which will combine Einstein's theory of gravity with quantum theory, the theory of the very small. We need a theory like that. This is a candidate for it, and it says basically that we no longer have point particles, but we have matter comprising tiny vibrating strings, and the different ways they vibrate gives you the different particles that we observe. Now, the problem is that after 40-odd years or so, string theory has made no predictions. Nothing that has been tested in the laboratory. Well, you might regard that as a weakness of the theorem, but Susskind and others see it as a strength. And what they say is, well, maybe there's a multiverse version of string theory, which gets called the landscape. And maybe there are 10 to the power 500 or solutions of this theory. And these solutions all get instantiated in different universes. So you get a multiverse version of string theory. Now, there are a number of other theories out there. The Big Bang itself is very well established, the basic paradigm. But what happens in the first tiny fraction of a second, and all this multiverse stuff is highly speculative. There are a number of other theories out there. So I have, at this point, a rather amusing quote from this exotic-looking Russian physicist, Nobel Prize winner. Incidentally, I saw this picture at the Russian Academy of Sciences in St. Petersburg a couple of years ago. We were doing a science and religion course, in the heart of militant atheism, as it was a few years ago. But anyway, be as it may. This is what he said: cosmologists are often in error, but seldom in doubt. There is some magnificent work being done, certainly at the observational level, extremely accurate, wonderful stuff being done. The theory is outstripping the observations, and that is a big problem. I'm going to run through what I see as some of the problems for multiverses. First then, that physics is speculative. To reach the kinds of energies that are talked about, that you need at the first 10 to the minus 43 seconds, you'd need an accelerator not 17 kilometers around like CERN in Geneva, but the size of the galaxy. CERN can take us back to maybe a billionth or trillionth of a second, which is astonishing with the Higgs boson and so on, but not back that far. There is a problem, as I was saying, about infinities. You can never complete an infinity. So any of these multiverses that have infinitely many universes, you can always add another. And you can't cover all the possibilities. Here's an infinite set, 1, 3, 5, 7, 9, 11. That's an infinite set of numbers. But none of those numbers has the property of evenness. So you can have infinitely many universes, but not guarantee that you have any with life in. To do that, you'd have to go for something that cosmologist Max Tegmark calls his level 4 multiverse, whereby he says that all mathematical structures have physical existence. Well, that's, to my mind, as metaphysical as you can get. It's at least as metaphysical as the idea of God, because how could you ever tell that any of those universes exist? There's a paradox, at least, about human identity, because as soon as you start multiplying things up by infinity, even though something like this room would be extremely rare, it would be duplicated elsewhere in the multiverse. And in some of those duplications, I would decide, right, I really am retired now. I don't want to come and give this lecture. And you'd be left with a blank screen, whatever. In other universes, I'd drop down dead. Well, I hope that isn't. We aren't not in that one before I complete the lecture, and so on and so on. It starts to get highly paradoxical. It doesn't, to my mind, rule them out. But if there is a simpler way of dealing with all these issues, then then surely that's the one to go for. I think the multiverse idea is not simple for that kind of reason. And also because, just going back to simplicity, William of Ockham, another great figure in the history of thought, really, talked about not multiplying entities needlessly. And it's been a principle of science that you take the simplest theory that explains your data and so on, with the fewest number of free variables or entities. Lack of predictability. We sometimes talk about God of the gaps, but I think there's a multiverse of the gaps. You find some strange feature in your laboratory. Normal science would say, well, I want to explain that in terms of the laws of physics or whatever, as we understand them. Maybe we might need to modify them. But a multiverse theorist could say, well, that phenomenon might be unusual, but in a multiverse, anything that can happen does happen somewhere, sometime. And indeed, if you start to think about order and disorder, then the number of disordered units, there are far more ways of being disordered than there are of being ordered, and this is a highly ordered, structured universe. And so we're more likely to be in disordered universes than ordered ones. The cosmological constant is the biggest problem in cosmology today, the biggest mismatch between theory and observation. You remember I showed you the curve, where the curve curved up? That's to do with what Einstein called his cosmological constant. It's like a negative gravity. It's pushing things apart, and it takes a constant value. So Einstein dismissed it once the Big Bang Theory came along. He introduced it to get a static universe. He didn't like the idea of an evolving universe either. He wanted an eternal universe. But anyway, he got rid of it later, called it his biggest blunder. But now it's come back on the scene. And the problem is that it takes a value that is far too small to be compatible with theory. Theorists think that the cosmological constant is to do with something called dark energy. energy of the vacuum. And when they calculate it, they get a value that's 10 to the 120 times too big. Well, if it were even 100 times too big, galaxies couldn't form in the universe. It needs to be that small. Fine-tuning is still required to some degree even to get a multiverse. As I was saying, these universes are in, they're really regions of a single overarching space. But that single overarching space, the mean density of that has to be less than the critical value for space to be infinite, according to Einstein's general relativity. So that's even still some fine-tuning to get an infinite space. And then there is a question about the amount of order in the universe. I was kindly given a glass of water. Now, if I were to drop this on the floor, the glass might smash, the water would go all over the place, and that's normal. That's what you see in the universe. You don't see water getting back into glass, the shards coming together, and glasses jumping up on tables, not unless it's a Harry Potter film or something like that. Now, the universe needed to be highly ordered at the very beginning in order for all the processes that I've described to occur, to give stars and galaxies and life. And Roger Penrose in Oxford calculated, using the term metaphorically though, the creator had of the order of 10 to the power 123 universe configurations to start from, only one of which resembles ours, has the order and structure of 100 billion galaxies out as far as we can see. So that is ultra fine tuning. Now you could explain that on the basis of a multiverse. Well, if all the, even it's a tiny probability like that, if you have infinitely many, you could explain it. But given a multiverse, we would be far more likely to find ourselves in a universe that is, as it were, good enough, fine-tuned enough for life, but not ultra fine-tuned for life. Universes in which there is a solar system surrounded by utter chaos would be very, very infrequent. 1 in 10 to the 10 to the 60 is the probability of getting one of those, but vastly, vastly more frequent than universes that are ordered and structured as far as we can see. So my analogy for that is the monkey sitting at a typewriter, eons and eons and eons on end. Suppose it eventually comes and writes, to be or not to be, that is the question, and that corresponds to a universe with life. The problem is, it's not the universe we're in. The universe we're in is more like the complete works of Shakespeare, on that analogy. Then, I think I'll skip fake universes. Serious philosophers and cosmologists think the multiverse is likely to give rise to far more simulations, matrix-type universes, than real ones. So I'll draw to a close by saying that theism explains why there is a universe at all. It explains why there should be life, because the Creator has purposes and intentions that it should do so, and creatures would be able to relate to him. God freely chose to create this particular universe, intending that it produce intelligent creatures. Of course, he could create others, and there are some in this world who Christians and so on who are perfectly happy with multiverses, but I tend to be a bit of a skeptic. God is more likely to create a universe with 100 billion galaxies worth of order than just the single solar system's worth of order. And now, coming back to a point that was made earlier on about by the bishop, there were two ways of arriving at the truth. I decided to follow them both, as my closing quote from Lemaitre. It's a both and! And I'll stop at that point and you can give me some questions.
Well, thank you very much, Rodney, and there's a very good demonstration of how science and faith can work hand in hand. Now we have about half an hour before lunch in which to ask Rodney any questions.
You didn't mention the many worlds interpretation of quantum mechanics as an alternative way of explaining a lot of the surprise.
Yeah.
What's your view on that?
Yeah, well, there are a number of ways in which cosmologists think about multiverses. The one I've described is one of the most popular today, in which they are different regions of an overarching space-time. Now, in quantum theory, the theory of the very small, you have this rather interesting role of the observer, who, and a quantum system is in a superposition of states. If you can get your head around this, it's like the cat in the box that is both alive and dead at the same time, and only when you open the box and make the observation does the cat. Well, it might be alive or it might be dead, but only does it collapse into one of those two states, because there's, what's going on is a quantum event, decay of an atom that triggers an explosion or something in the box. Or the famous two slits experiment. You pass light through two slits and you observe what happens on a screen. You do the same with particles and you find you get diffraction patterns, but then you find that the only way to explain what's going on is to say that the particle or the photon went through both slits at the same time, and where it actually lands is determined only when the observation is made. But is it made by the observer or is it made by the screen? These are all sorts of interesting phenomena. Now, so the usual sort of Copenhagen interpretation of quantum theory says, yeah, you get the superposition of states, and when the observation is made, the universe collapses, where the wave function, so-called wave function, collapses so that you end up with one of these states. So a few years ago, someone called Hugh Everett came up with a multiverse version of quantum theory in which he said that, no, it doesn't, the wave function doesn't collapse. We just hive off into a universe in which we observe the one of the collapses, and then the universe itself splits. And it splits many, many times. It splits time after time after time. And you get all these universes, which of course don't interact with each other, but they all exist. So there are people who favor that today. My old friend David Deutsch, who does work in quantum computing, favors that. So there are some people who opt for that. Now, of course, then what you've got to add into that in order to get to solve the fine-tuning problem is that the constants of physics alter when the wave function collapses. And that seems to me to be an extra added hypothesis. So it's another way of getting a multiverse, and I think it suffers from really the same kinds of problems that the main one I've talked about suffers from.
Great, thank you. Now yes, person at the back.
It said that the universe began with a singularity.
Yeah.
I've always been puzzled by precisely what that means. A state of infinite density, not quite sure what that is.
Yeah.
Could you just say why a singularity is tantamount to nothing, if indeed it is tantamount to nothing?
Well, I mean, the problem, you see, these singularity theorems track back I think it's easier to think of tracking back the history of a virtual particle or photon and finding that it comes to a stop. Yes, the singularity is really where that you get infinite density, infinite mass, and so on. And the problem is that you don't know what the physics to apply to that is. I mean, physics tends to, not like things when things blow up to infinity. And whether the singularity is avoided by some of these other theories, like string theory and so on, well, that's a moot point. I mean, but a black hole is a sort of singularity in another sense, and that's where, because we're going forwards in time, but we're having matter go across the horizon. It's lost. You can't. No signals can get out, and then it contracts into a point. Well, quite what's going on at that very point, who knows? But Hawking now thinks that information. Well, I think he keeps changing his mind about whether information comes back out of the black hole. I think he thinks it does now, because he did for a time think that and some people still think that you have a multiverse created through black holes, and they go. What happens at the center is that another universe is spawned and completely distinct from this one. It is hived off from ours. So singularities are are very difficult to get your head around. But they do mark a beginning. That's, I think, in terms of this universe, I think as Vilenkin says, the singularity at the beginning does mark a beginning. I mean, people used to have Big Bang, Big Crunch ideas. On Roger Penrose's argument, if you have a big crunch, then that doesn't create the right conditions for another bounce, because it's completely asymmetric from the beginning. It's completely disordered. Anyway, it's probably enough on singularities.
It's reassuring to hear that you find it hard to get your head around singularities, Rodney, because I, as a biologist, certainly find it difficult to get my head around. So, on that note, are there any non-physicists who would like to ask a question? Please don't be shy. No question is too simple. If you can wait for the microphone. Yes.
I'm glad you said that no question is too simple. What is a multiverse? And what are the properties of a multiverse?
Well, a multiverse is a giant collection of universes. That's really the idea of a multiverse. The idea is that all these constants of physics that I'm talking about, say the strength of gravity, takes all the values it can take. So it takes all the values between 0 and 10 to the 40. And there might be other universes where the laws of physics are different, and so on. So a multiverse says that all these universes exist. And because they exist, our universe, with the properties it has, exists. It's just one of this giant collection. That's basically what a multiverse is. Going back to the other question, I can just go back to that for a minute. Hawking's very interesting no-boundary proposal is meant to avoid a singularity. That's a theorem that's meant to avoid a singularity. He says that space-time gets smoothed out at the beginning. But what actually happens is that the universe starts at the point where his four-dimensional space merges with the three dimensions of space and time. So if you read Hawking's technical papers on this, what you find is that the universe began with a very tiny sphere. And he also says you can believe what you like about the reality of the imaginary space, and whether that's real or whether real time is real and imaginary time is imaginary. So that would be a kind of consistent and philosophically reasonable way of thinking about his no boundary proposal, I think.
Right. Any more questions? Yes, the person in the check shirt, and then we'll come.
I hope that it's not too off the topic, but I would like you to comment on how discovery of life out of Earth would impact on Christian thinking and specifically on this theistic fine-tuning.
Yeah, so life elsewhere in the universe, you say?
If life were discovered out of the Earth?
Yeah. Well, that's a very interesting good question. The fine-tuning basically gives you the conditions for life to exist anywhere. So it really doesn't comment on how many times life has come into existence, evolved into intelligent life in the universe. There are a lot of arguments about this, and one of the interesting developments in cosmology certainly is some of these sort of very fine observations that are happening at the moment in astrophysics are to do with detecting exoplanets, planets going around other stars. It's brilliant work, really, because you're detecting a tiny, tiny drop in the luminosity of the star as a planet goes in front of it, and that sort of thing, or a tiny wobble in the star as the planet goes around its orbit. And most of the planets discovered that way are Jupiter-like planets, gas giants. We have now discovered a handful of planets that are in the so-called Goldilocks zone, right region around their star, and so on, for life. And a few years ago, a chap called Frank Drake wrote down an equation working out how many civilizations there were in our galaxy by multiplying a string of numbers together, a lot of probabilities and so on. And the trouble is that some of those numbers critical numbers, we simply don't know why, what the probability of life getting going in the first place is on the right kind of planet, what the probability of that developing into intelligent life is, and so on. A few years ago, Enrico Fermi, who was working on the hydrogen bomb, as a sort of distraction from such things over lunch, speculated on, okay, why aren't they here then? And he did a sort of simple back-of-the-envelope calculation on how long it would take for civilizations to develop and basically colonize the galaxy. And we should have seen them by now if they were here. Okay, but be this as it may, what are the theological implications? Well, of course, God could certainly create life abundantly in the universe if he so chose. And the main theological question is then how, it seems to me, what we do about the incarnation. Are we uniquely privileged in having God reveal himself to us in the person of Jesus Christ, to live a human life, to die for us, for our sins, and so on, and to rise again? Are other creatures fallen? Do they need a saviour? Well, even if they didn't, it would be rather puzzling that we had this unique privilege of God revealing himself just to us. Now, this has been thought about theologically, and the Anglican theologian E.L. Maskell in the 50s thought about this particularly, and what incarnation meant in terms of the Chalcedonian definition and so on, and that God could, as it were, take on the nature of other intelligent creatures, just as he has human nature. Disputed. Brian Hebblethwaite here in Cambridge disputes that. So, but that I think is the main question.
Thank you. Now I had a question here, and then we'll go over to the other side of the room. So, the person in the grey jumper.
Just a quick question. Carl Sagan says that the cosmos is the only thing that there is, and it's the only thing that there will ever be, right? So, just in your opinion, what do you think is the main difference with the theory of the God of the gaps? And can't we just say that we've come such far away with science? Can't we say that one day as well we'll discover why this fine-tuning is, and we don't really need the God?
Yeah. Funnily enough, the dean of this college agrees with Carl Sagan, but he agrees with it in terms of his view of God isn't a thing, sort of thing, if you follow that line of argument. However, in terms of, I think it's a very important question as to whether this is a God of the gaps argument, like the bacterial flagellum in intelligent design, and so on. And I think it isn't, because when what the intelligent design, capital I, capital D people are doing is saying, well, we've got the process, you've got a theory of evolution. It can't explain this particular structure in the universe. It can't explain the bacterial flagellum. It can't explain the human eye. Well, it can, and it has. That kind of gap gets filled in. And we now know that eyes, of one form or another, have evolved 20 different times in the evolutionary process independently, in independent strands of evolution. But this is a rather different question. This is not saying, well, given the laws of nature, what can they or can't they explain? But why do the laws of nature take the form the laws of nature take? It's a sort of meta-scientific question. The ID question is still in the realms of science. This is really metaphysical, it seems. Why these laws of nature? Why do the laws of nature take the form they do with the results that they have? So I think it's a fundamentally different question.
Yes, the gentleman in the pale-coloured shirt.
Thank you. My question is not unrelated. You closed by talking about the virtues of the theist hypothesis, but it seemed to me that an argument that the universe has been set up right at the beginning by a creator is a deist argument rather than a theist one. And in terms of an engagement between faith and science, the idea that God, who is spirit, continues to engage with the universe, which is matter, and in ways that make a difference to what happens, that seems to me much trickier. And what you've talked about isn't inconsistent with that,
Yeah.
but doesn't really engage with it.
Yeah, well, there's some truth in that. I mean, this argument gets you so far. And of course, I did criticize Hawking's view of his doctrine of creation, which was simply deist, to light the blue touch paper, and saying that Christians want to say that the universe is, God is interacting with the universe throughout its history. So I certainly would want to say that. But this is only one argument. This is only part of the story. It only gets you to, what kind of God does it reveal? Well, a God with certain attributes, perhaps. A super intellect, a great powerful God, and so on. But it doesn't get you to the God and Father of our Lord Jesus Christ. It doesn't get you that far. I mean, it's not, as you say, it's not inconsistent. For me, it's a first step. I mean, I want to get people to come to know Jesus, ultimately, that's the point. But for those for whom science is a blocker, this is a way in. It's a way in. Another argument that's been on my mind for a while, though, and I half referred to it there, is to do with the principle of induction, which is that we live in a universe which is ordered and whose order persists. The sun rises each day. We believe the sun will rise tomorrow. Now, this was a big problem for the philosopher David Hume, who was an atheist. And it is a logical conundrum. How can we believe the future on the basis of the past? And on the basis of a multiverse, or universes which go astray from order, they could go astray from this in any number of ways, infinitely many ways, in an instant. So the fact that order, that this order persists in the universe, to me is a pointer to there being a mind behind the universe sustaining its order, which goes a bit further than deism. Certainly, that God is sustaining the universe in being with the order and structure that it has. And so it's God's faithfulness, if you like, his reliability, with the seasons recurring and so on, as you get in Acts 14.
Right, now we have a few more minutes. Can I see a show of hands of anyone who has a question left? If you raise it very high, then I can plan my route around the room. Yeah. Okay, so we've got one. Did you have a question? And then 3 more. Okay, we'll see how many we can get through. In fact, let's start at the back, seeing as we haven't had a...
Okay. Most of our information about the universe is based on photographs. But how can you read a photograph when a normal photograph is 2 dimensions of 3, but due to the properties of light, you're going to get 2 dimensions out of 4 because you've got the time difference for each patch of light that's you're hitting.
Well, yes,
so
of course.
You're ending up with something that's you're going through that way as well as that way.
Yeah.
You understand where I'm going from?
Well, of course, I did give you that diagram, didn't I? Whether I can go back, which is shows you the dimension. Where was he? Yeah. Of course, this is collapsing 3 dimensions sort of into 2, because this is meant to be cylindrical, if you like. So you've got 2 space dimensions in that diagram and 1 of time. But when you look at a photographic plate like the one I showed earlier on of the Hubble Deep Field, I mean that is the light has taken 13 billion years to reach us. So that's a snapshot of the universe as it was.
I've heard. Sorry, can you hear me? I've heard the fine-tuning argument refuted with something that goes along the lines of, if I said I had to live in a box of precisely the dimensions such that the volume was 8, and so it's 2 by 2 by 2, and if you move any one of those sides by any really tiny amount, then clearly I no longer live in that box that's that size, so it won't work anymore. But the argument goes, but if you decrease one of the other sides, you can still end up with the same volume. Do you see what I mean by the analogy?
I think I do.
So the answer, what they're saying is, if you change the gravitational constant by a small amount and then change something else then there must. So it's not that improbable after all.
But actually,
is that a valid argument? is my
well,
question.
I think it's no,
I don't know.
I don't think it's valid, but yeah, because actually you've then also increased. Basically, instead of having a line on which, say, you know, one of the variables can be between there, and it, you know, it has to be in that range for life. That if you have a two-dimensional graph, you then get more like a cone. And in fact, what you tend to find is that the overlaps between these different cones in the multidimensional space is tiny. You know, you still get, or in fact, even more so, because you're increasing the volume possibility as well as of the possibilities, as well as the volume that's required for, you're changing the volume required for life. So, you know, a multidimensional look at these things, it certainly doesn't solve the problem. It makes it worse.
Great, thank you. And if just one last question with the gentleman in the blue jersey. Thank you.
This is probably going to be the most ridiculous question of the whole 2 days, but I mean, has there been any thought as to how God created singularity, how he could create matter? I mean, it's probably an impossible question.
Yes. Yes. How God created, then I think I leave aside. That God created, I think, you know, we can make good arguments for, but.
So this is something we have to accept
and the need for
faith,
God,
really,
the need for something, the need for there to be something. You know, if there is only ever nothing, then there only ever will be nothing. So there needs to be. This is my argument for the necessary being, but I don't explore how God actually created a singularity.
No, I just wondered if anyone had given any thought to that, as far as you're aware.
I mean, if you go back to Plato, of course, he had matter that's eternal, coexistent with the demiurge, and that matter is resistant to the demiurge. Yes. I mean, Christians have wanted to get away from that picture. You know, everything is dependent on God for its existence, and it doesn't resist.
I thought I'd ask it, didn't I?
But yeah, no.
We have time for one more question, seeing as that was a slightly easier one to answer. Maybe we come to the front. If you still have did you still have a question, or we can? Oh, if you can wait for the microphone to come to you, would you like to pass it forward? Sorry, our microphone is just distracted. Thank you.
I was interested in what you were saying earlier about the possibility of life on other places. I happen to think that our chances of discovering a small enough planet within any sort of range that we could come across is probably infinitely minute, and that will not happen. But having read the kind of thing that Simon Conway Morris writes about the way that evolution goes and develops the way that life can use all kinds of resources that are around, and eyes appear because there are light waves to be discovered by an organism. Yes. That hearing evolves in all sorts of ways because there are things to be heard, etc. Yes. When you start following the way that he explores that, you have to say, if there were another planet on which something were to evolve, then it might even become conscious like us.
Yes,
don't you?
Yes, I agree with that entirely. And you know,
whether we'll discover it.
Yes, no, I agree exactly with that analysis. What's the subtitle of his book? Inevitable Humans in a Lonely Universe. Yeah. So if life gets going, which of course is the difficulty, and if it develops to intelligent life, which again, you know, the probability, we don't know what the probability is, it could be very small, but anyway, if it gets there, then it will be something not so dissimilar from us in the end.
Great, great. And of course now he disagrees with the Lonely Universe part. He realises that he may have been wrong on that point. So yes, he does cross that part out on the front of his book cover when he now displays that on his slides. So it's really interesting, and he's excited about that, to see the way that science is changing. So thank you so much, Rodney, for working very hard. And I'm sure if you didn't get to answer your question, you'll be able to quickly answer it, so long as Rodney can actually get his lunch at the same time. So thank you so much.